Every bridge you have crossed, every tower you have entered, and almost every machine that moves modern life shares one basic ingredient: steel. It is strong, cheap, weldable, repairable, and produced at a scale no advanced material has ever matched. Entire cities were designed around it. But in northern China, engineers have begun producing a black fiber thinner than 1/10 of a human hair that can be more than 5 times stronger than steel while weighing roughly 1/4 as much. The surprising part is not that carbon fiber can beat steel in a laboratory. That has been known for decades. The breakthrough is that China is now moving ultra-high-strength T1000 grade fiber out of small experimental batches and into continuous industrial production. Stick around, because by the end of this video, you will understand exactly where this material can replace steel, where it cannot, and why the manufacturing scale matters more than the headline. Before we continue, subscribe and turn on notifications if you want clear engineering stories without the empty hype. Steel earned its position honestly. A typical structural steel has a density close to 7,850 kilograms per cubic meter. That sounds abstract, so picture a solid steel cube 1 meter wide, 1 meter deep, and 1 meter tall. It would weigh almost 8 metric tons, roughly the mass of 5 average passenger cars stacked into a space smaller than a wardrobe. That weight is not always a disadvantage. It gives buildings stiffness, provides machines with stability, and helps bridges resist vibration. Steel can also bend before it breaks, which gives engineers a visible warning when a structure is overloaded. More importantly, steel is not just a material, it is an industrial system. Iron ore is mined, processed, reduced, melted, alloyed, rolled, cut, welded, inspected, repaired, recycled, and sold through a global network that has been refined for more than a century. In 2025, the world produced about 1.85 billion tons of crude steel. China alone produced roughly 961 million tons, more than half of the global total. Compare that with even the most ambitious carbon fiber lines, which are measured in hundreds or thousands of tons. Steel operates on a scale that carbon fiber does not yet approach. That scale explains why steel can be found in a cheap washing machine and a billion-pound bridge. It can be formed into sheets thinner than a coin, beams taller than a person, cables longer than a city street, and gears that survive millions of load cycles. When a steel part cracks, technicians often know how to detect it. When it bends, it may still carry some load. When it reaches the end of its life, it can be melted and turned into new steel. Scrap-based steelmaking can require only a fraction of the energy used to produce steel from iron ore. But the old world has a hidden cost. Steel is heavy, and every kilogram carried by a car, train, aircraft, robot, or rocket demands energy. A heavier electric vehicle needs a larger battery to travel the same distance. A heavier aircraft burns more fuel on every flight. A heavier robotic arm requires larger motors, stronger bearings, and a more rigid base. The penalty does not stop with the original part. Weight creates more weight. Then there is the climate cost. Iron and steel production accounts for roughly 7% of energy sector carbon dioxide emissions. Traditional blast furnaces depend heavily on coal, not only to generate heat, but also to remove oxygen from iron ore. Steel remains essential, and cleaner steel making is advancing, but replacing even a small percentage of steel in weight-sensitive applications could reduce energy use far beyond the factory gate. For decades, carbon fiber looked like the obvious answer. A filament is mostly carbon atoms arranged in tightly bonded microscopic structures. Along its length, those bonds resist enormous pulling forces. but one filament is too thin to become a useful beam, panel, tank, or vehicle body. Engineers group thousands into a tow, combine them with resin, and arrange the fibers in chosen directions. The fiber carries tension. The resin holds the shape, transfers load, and protects the fibers. Carbon fiber is not a metal replacement in the simple sense. You do not melt it, pour it into a mold, and receive a stronger steel part. The useful material is usually a carbon fiber reinforced polymer composite. Performance depends on the fiber grade, resin, layer direction, curing process, shape, defects, and joints. A poor composite made with excellent fiber can still fail. The strongest laboratory fiber also does not automatically become an industrial product. Most high-performance fiber begins with polyacrylonitrile, or PAN. It is mixed into a spinning solution and pushed through a spinneret containing thousands of microscopic holes. The filaments must be nearly identical. A tiny variation in thickness, contamination, stretching, or heating can become the point where the final fiber breaks. After spinning, the precursor is stabilized in air so it will not melt during carbonization. Conventional stabilization can take about 80 to 120 minutes and has long been a major energy and cost bottleneck. The fibers then enter low oxygen furnaces at high temperature. Most non-carbon atoms leave, and the remaining structure becomes tightly organized carbon. The difficulty rises as the target strength rises. T700 grade fiber is already strong enough for many industrial uses. T800 pushes performance higher. T1000 demands even better control of defects. A microscopic flaw that seems irrelevant in an ordinary plastic thread can become the exact point where an ultra-high-strength carbon filament snaps. Making a few perfect meters is one problem. Making kilometer after kilometer across 12,000 filaments at once, every day, with stable strength, is a completely different problem. That is the part China has been attacking. In Datong, Shaanxi Province, a project involving the Institute of Coal Chemistry under the Chinese Academy of Sciences and Shaanxi Huiyang Carbon Material Technology brought a 200-ton per year demonstration line into operation. The line produces 12K small-tow T1000 grade carbon fiber. The term 12K means each tow contains 12,000 individual filaments. Small tow fiber is harder and more expensive to produce than large tow industrial fiber, but it offers greater control and more uniform performance for demanding components. The reported filament diameter is about 5 to 7 micrometers. A typical human hair is roughly 10 times wider. The reported tensile strength exceeds 6,400 to 6,600 megapascals. Tensile strength is the pulling stress a material can withstand before breaking. In plain English, these fibers resist being pulled apart with extraordinary force. A 1-meter bundle from the Datong line has been described as weighing about half a gram while supporting more than 200 kilograms under a controlled tensile demonstration. Half a gram is about the mass of a small paper clip. 200 kilograms is roughly the combined mass of 3 adults. That comparison does not mean you can hang 3 people from an unprotected thread in the real world. Knots, bending, abrasion, shock loads, and imperfect grips change the result, but it shows the scale of the material's strength along its designed load direction. The process breakthrough includes dry jet wet spinning. The name sounds contradictory, but the idea is straightforward. The polymer solution exits the spinneret through a short air gap before entering a liquid coagulation bath. That air gap allows the filaments to stretch and align before they solidify. Better molecular alignment can improve strength and surface quality. The liquid bath then fixes the fiber shape. Every variable matters: solution purity, viscosity, spinneret geometry, air gap length, bath chemistry, draw ratio, temperature, line speed, tension, oxidation, carbonization, and surface treatment. But here is the part that will really mess with your head. The 200-ton line is not the end of the story. It is evidence that the process can survive outside the laboratory. The broader project has been described as moving toward a 1,000-ton scale. In June 2026, another Chinese producer, Zhongfu Shenyang, started a 1,000-tonne high-strength T1100 grade line alongside other carbon fiber lines in Jiangsu. Around the same period, Sinopec Shanghai Petrochemical announced stable batch production of 12K T1000 grade fiber using a wet spinning route, with reported tensile strength above 6.5 gigapascals and tensile modulus above 300 gigapascals. Tensile modulus measures stiffness, not breaking strength. A material can be strong but stretch too much, or stiff but brittle. For precision structures, both numbers matter. Above 300 gigapascals means the fiber resists elastic stretching at a level comparable to or above many steels along the fiber direction. Yet because carbon fiber composites are directional, that performance does not automatically exist sideways through the material. Engineers must place the fibers where the forces will travel. Think about that for a second. China is not relying on one machine or one organization. Multiple teams are developing high-strength grades, different spinning routes, and larger production lines. That creates an ecosystem of precursor chemistry, furnaces, process controls, resins, automated placement equipment, inspection systems, component designers, and customers willing to certify the parts. Now look at the numbers that make steel replacement tempting. Steel is roughly 4 times denser than carbon fiber. In an ideal weight-sensitive structure, replacing a steel component with a well-designed carbon composite can cut the component mass by 50 to 75%. The United States Department of Energy has estimated that a 10% reduction in vehicle weight can improve fuel economy by about 6 to 8%. For an electric vehicle, the benefit appears as longer range, a smaller battery, or room for additional safety and electronic systems without increasing total mass. Imagine a structural assembly that weighs 100 kilograms in steel. A composite version will not simply weigh 25 kilograms because geometry, stiffness, impact protection, fasteners, fire requirements, and manufacturing rules all matter. But even a reduction to 50 kilograms removes the mass of an adult passenger from the vehicle. That reduction then permits smaller brakes, lighter suspension components, or a smaller motor. Weight creates more weight, but weight savings can also create more weight savings. Aircraft show the effect even more clearly. Well-designed composite aircraft structures have historically delivered weight savings of around 25 to 30% compared with optimized metal structures. Every kilogram removed can be traded for additional range, payload, or fuel savings. In rockets, the value of mass is even higher because the vehicle must accelerate not only the payload, but also the fuel needed to accelerate the fuel. A lighter pressure vessel, fairing, interstage, or structural panel can change the entire mission design. High-pressure hydrogen storage is another target. Hydrogen has low density, so vehicles store it at very high pressure. The tank must resist enormous internal force without becoming impossibly heavy. Carbon fiber wraps provide the strength, while a liner contains the gas. In these tanks, the fiber can represent a large share of the cost. Cheaper, reliable T1000 grade material could improve storage systems for fuel cell vehicles, heavy transport, industrial gas, and aerospace applications. Wind turbine blades already use large amounts of composite material. As blades grow longer, carbon fiber can stiffen critical sections without the mass penalty of steel. Rail vehicles, drones, robotic arms, satellites, medical imaging tables, sports equipment, and industrial rollers all benefit when stiffness and strength must come with minimal weight. And this is where it gets strange. China is already the world's largest steel producer, but it is also building the material systems that could remove steel from selected premium applications. In 2025, Chinese steel output was about 960.8 million tons. A 200-ton T1000 line is only about 0.002 of 1% of that figure. Even a 1,000-ton line is microscopic beside the steel industry. So the phrase "steel obsolete" is obviously not a volume forecast. It is a value forecast. Carbon fiber does not need to replace hundreds of millions of tons to disrupt important markets. It needs to replace steel where each kilogram matters most and where customers pay for performance. A ton of structural steel and a ton of aerospace-grade carbon fiber do completely different jobs and occupy completely different price categories. The strategic question is not how many tons exist. It is which components become possible, cheaper, lighter, or domestically available because the material exists at reliable scale. Hold on. Because the next number is the one that matters. The first Datong line is rated at 200 tons per year, while the wider project aims toward 1,000 tons. That is a 5-fold scale increase. Zhongfu Shenyang's new high-strength line is also rated at 1,000 tons annually, and it sits beside a 5,000-ton large tow line and a 600-ton high modulus line. Those 3 lines cover 3 different market needs: lower cost volume material, very high strength, and very high stiffness. This product spectrum matters because no single carbon fiber grade replaces every metal. A drone arm wants low mass and stiffness. A pressure vessel wants tensile strength. A satellite may need dimensional stability. A robot may need stiffness with rapid acceleration. A car body needs crash performance, fast cycle times, repairability, and low cost. Building the entire range allows engineers to choose instead of forcing one expensive fiber into every job. The manufacturing race also explains why competitors are paying attention. Japan built an early lead through companies such as Toray, Teijin, and Mitsubishi Chemical. The United States and Europe developed deep expertise in aerospace composites, resins, automated placement, and certification. China initially depended more on imported high-end fiber and equipment than invested across institutes, chemical companies, and composite manufacturers. The reaction is not panic. Engineers do not abandon certified supply chains because of one announcement. Aerospace qualification can take years. Automotive teams may test thousands of parts through heat, moisture, impact, vibration, and fatigue. But procurement teams notice when a strategic material gains another supplier. Competitors notice when output grows from laboratory kilograms to industrial tons. Commercial pressure may appear first below the aerospace tier. Drones, robotics, industrial machinery, rail components, sporting goods, and performance vehicles can adopt new suppliers more quickly. Each lower-risk product generates production experience, quality data, revenue, and confidence. That learning curve can reduce waste and improve consistency. Cost is the wall that still protects steel. Carbon fiber manufacturing begins with expensive precursor chemistry and uses tightly controlled thermal processing. Stabilization and carbonization require large equipment, energy, time, and precise atmosphere control. The fiber then has to become a composite part. Layers may be cut, placed, infused, molded, cured, trimmed, drilled, inspected, and joined. Some aerospace parts cure inside enormous pressurized ovens called autoclaves. The equipment is expensive, and the production cycle can take hours instead of seconds. Steel stamping is brutally efficient. A press can form a body panel in moments. Welding robots can join structures rapidly. Repair shops understand dents, cracks, and corrosion. Steel supply is available almost everywhere. Carbon composite repair requires trained technicians, controlled materials, and careful inspection because damage can hide between layers. This is also where the headline breaks down. Carbon fiber is strongest, mainly along the direction of the fibers. Steel is much more uniform in every direction. A composite part can be designed to carry expected loads with extraordinary efficiency, but an unexpected impact from the wrong direction can damage the matrix or separate layers. This separation is called delamination. It may occur below the surface where the damage is difficult to see. Carbon fiber is stiff and strong, but it usually fails with less visible plastic deformation than steel. Steel can crumple and absorb energy. A composite can be engineered for crash absorption, but it does so through controlled fracture and crushing, which demands very specific design. Fire performance depends heavily on the resin system. High temperature can soften, decompose, or burn the polymer matrix even when the carbon fibers remain intact. Joining is another problem. You cannot weld a carbon composite to steel with an ordinary welding torch. Engineers use bolts, rivets, bonded joints, molded interfaces, or hybrid inserts. Drilling holes cuts fibers and creates stress concentrations. Adhesive bonding needs clean surfaces and controlled curing. When carbon fiber touches aluminium in the presence of an electrolyte, such as salty water, galvanic corrosion can attack the metal unless the materials are electrically isolated. Recycling remains difficult. Steel can be sorted and remelted through a mature global scrap system. Thermoset composite resins are designed to cure permanently. Recovering clean, high-value fiber without destroying too much of its performance requires mechanical, thermal, or chemical processes that are still developing. Recycled carbon fiber is useful, but it may not return directly to the same highest performance application. Carbon fiber production is not automatically clean. PAN comes from chemical feedstocks, and the ovens use substantial energy. Resin chemistry, manufacturing scrap, and end-of-life treatment affect the result. A lighter vehicle can save energy during use, but the full life cycle must be measured. Replacement makes environmental sense only when operational savings and service life justify the production impact. Here is the thing. None of those limits cancel the Chinese breakthrough. They define it. The achievement is not a magical black thread that replaces every beam, bolt, rail, and ship plate. It is the transition from knowing how to make an exceptional material to learning how to manufacture it reliably, repeatedly, and in useful quantities. A laboratory record proves physics. A production line proves process discipline. Multiple production lines begin to prove an industry. That distinction is why the phrase engineers are calling it impossible feels believable even when the real engineering language is more cautious. The impossible part was never simply reaching 6.5 gigapascals once. The impossible part was controlling thousands of filaments, microscopic defects, chemical purity, thermal history, tension, and surface treatment across continuous production without the quality drifting out of specification. One small variation can move through the entire line and ruin material that looks perfect from the outside. The first promise of this video was to explain exactly where this material can replace steel. The answer is now clear. T1000 grade carbon fiber can challenge steel in structures dominated by tension, stiffness, corrosion resistance, and weight. It makes the strongest case in aircraft, spacecraft, drones, pressure vessels, robots, rail systems, wind energy, and selected vehicle components. It becomes less convincing when low cost, high temperature, impact tolerance, easy repair, isotropic performance, welding, and mass recycling matter more. So steel is not disappearing. In fact, the energy transition will require vast amounts of steel for grids, wind towers, factories, vehicles, railways, and new infrastructure. The world produced about 1.85 billion tons in 2025 because no other structural material combines cost, scale, versatility, and recyclability in the same way. But steel is losing its automatic right to every demanding job. For more than a century, engineers often began with steel and asked whether anything else could justify replacing it. The emergence of reliable T1000 and T1100 production changes that starting point. In weight-critical systems, engineers can begin with the load path and ask whether metal is still necessary. That is a subtle shift, but it can redesign entire machines. Return to the image from the beginning. A black bundle thinner than a shoelace, built from 12,000 filaments, with a 1-meter sample weighing roughly half a gram and supporting more than 200 kilograms in a controlled pull. That is not a metaphor. That is just the math. Now multiply it by continuous production, domestic equipment, multiple factories, thousands of tons of planned capacity, and a national manufacturing system that already builds aircraft, electric vehicles, drones, wind turbines, trains, ships, satellites, and industrial robots. That is why the breakthrough matters. It is not a scare story about steel vanishing tomorrow. It is a warning that material advantages, once limited by scarcity, can become industrial advantages when scale, consistency, and supply security arrive together. China has not made steel obsolete.